Hi, in this video I want us to take a second look at the basic properties of compound interest, and we will do so while once more comparing compound interest to simple interest. I will be using Microsoft Excel for this analysis. If you are not familiar with this application, maybe this video will serve as an introduction to the capabilities of Excel. I urge you to try and replicate what I've done here and to explore other finance questions using Excel. So let's get started. We'll assume a principal value of $1. In this discussion, we'll maintain the nominal value of the compound interest equal to the annual simple interest rate. So let me introduce you to Excel's formulas. To keep these values the same, what I've done is I write the value of the interest rate, the simple interest rate here, and here I just write a little formula, equal D3. What that means is whatever I write in here will also show up in here. So if I change this to 6%, notice this automatically becomes 6, and of course everything updates. So let's change that back to 5%. We'll start with frequency of conversion of once a year, and we'll calculate the interest rate per compounding period. So this is for simple interest, and these three have to do with compound interest. Here is the formula. I simply divide the nominal interest rate by the number of compounding periods per year. This means that as I go changing this value here, let's suppose I go 12 compounding periods per year, notice the interest rate per compounding period automatically is increased. So Excel is a very powerful tool, and you can use Excel to answer questions that can be fairly complex, and you can do so fairly efficiently. I now want to go over how to do all these calculations. So first we want to put in the year. So we started year 0, then year 1, and I can just grab this like this and drag it down, and let's say we're going to do for 20 years. As easy as that. Then for the simple interest, I type in the formula for simple interest. So here it is. This is the principal. Notice D2. So these dollar signs mean that this is an absolute reference, which means when I copy this formula here, I want it to still reference this value here. If I didn't have dollar signs, then it would think that it should get the principal value from this cell, which of course it shouldn't, because this is the interest rate, the simple interest rate. So it's P times, notice in Excel you have to put a little times sign, it's an asterisk. Notice how everything is written in linear form. So it's very important you know how to write out equations in linear form. 1 plus the interest rate, which is R here, 5%. So inside of Excel this is recorded as 0.05, so be careful. When you do this, you don't write 5 in your calculator. This is really 0.05. It's just that Excel has that in the background. And then of course times the time, which is this value here, the number of years. Notice there is no dollar sign here, because when I copy, I want the formula to use the next value. So I just do like this. And of course I could copy this down. So if I copy it here, let's take a look in here. Notice it's still using this as the principal and this as the interest rate, but now the time is F3. Notice here the time was F2, now F3. Of course, to copy all of these down, all I need to do is double click right here. So notice it becomes this dark plus sign. I double click and I'm done. Let's do compound interest. I type in the formula, and once again notice it's the principal 1 plus, but now I'm using the interest rate per compounding period, which I have calculated here. Now I could put right in here the little expression for how you get the interest per compounding period, which is the nominal interest rate divided by the frequency of conversion. However, I have already calculated I here, so I just make a reference to it here. And again, I want to, in each one of these cells, reference this very same cell, so it's an absolute reference. So again, the dollar signs. Then I'm going to raise it to the frequency of conversion and number of converting periods per year, which is this value here, and notice that's going to be fixed. It's always going to be that value for all these calculations. Of course, the year will vary, so that doesn't carry the little dollar sign. So this is not an absolute reference. I do like that, and I get, notice at the end of a year it's the same thing. So now all I have to do, I can drag all of this down, but I can just double click also and see how easy we do that. So we have our calculations. Now we would like to draw some kind of a graph. All I do is I select this. Now it won't always be possible to do that, but here in this case it's fairly easy, and I just pick one of the recommended charts. You will need to, as you get more advanced in using Excel, know how to build it from scratch and not just pick one of the ready-made charts. But for now we can just go with this ready-made chart, and notice we have our chart. I can maybe change this to simple interest vs compound. I can make this a little bit bigger if I so desire. And we're ready. Watch how easy. So I urge you to learn to use Excel. To be proficient at using Excel, you need to know to write little formulas in linear form. Let's take a closer look at our results. At 5% interest every year, this $1 increases by 5 cents. And we can see that at the end of 20 years, well, it's worth $2. In the case of compound interest, at 5% compounded once a year, we have that at the end of 20 years, that $2 has grown to $2.65. So here in this graph we can see the difference between the growth at simple interest and at compound interest. If you remember, this sequence of values here forms an arithmetic progression. Arithmetic progressions give us what is called linear growth. If we look at compound interest, this list of values forms a geometric progression. Geometric progressions give us what is known as exponential growth. So this equation represents linear growth. This is a linear equation. This equation represents exponential growth. In other words, this is an exponential equation. Let's increase the rate of compounding from, let's say, once a year to 12 times a year. See now that $1 now has a future value of $2.71. If we increase this to 52 times a year, at 52 times a year, it grows to about $2.72. Let's go for 365, and we see it grows to 2.718. So let's bring this back to say 12 times a year. Let's change the interest rate to, let's say, 15%. Now you'll see the dramatic difference between these growths. At the end of 20 years, we have $19 here. This $1 has grown to $19.71, while at simple interest, the $1 has grown to $4. Alright, so I recommend that you do something like this and experiment with these values to get a sense of the difference between compound interest and simple interest, and how the frequency of compounding affects the future value in compound interest. Let's bring this to 100%. Let's use a frequency of conversion of, say, 1000. Just thought you might find this curious. Notice the huge difference now between simple interest and compound. Simple interest compared to compound interest looks like a flat line here. At the end of 20 years, at 100% compounded 1,000 times a year, that $1 is $480 million under compound interest, whereas under simple interest it's just $21. But let's take a look at this number here. After 1 year at 100% compound interest, it's 2.716. Let's raise this to 10,000. 2.718. 100,000. So this number is very important. It's a future value of $1 at 100% interest rate when the frequency of compounding is very large. If we could make this an infinitely large number, what would this be? So I'll leave you with that. Okay, so that's the end of this little video. I hope it has been helpful in some way. Bye for now.